Okay, welcome BC to what I call day one on this in this book we have. So today we're going to be learning about a thing called limits, and this is something that almost all pre-calculus classes give an introduction to limits, and the amount they do vary from school to school. But I'm just thinking because some schools may not have it in their content, and more importantly, or more pressingly, that COVID might have affected schools' ability to get to this, that I have to assume that some of you have never seen limits before. So if you've seen them before, today is going to be a little more reviewy, but it's just to make sure that we're all starting off on the same page. So let's get to it. So last time, if you remember, we looked at these expressions, and we looked at average rate of change and slope, but then we also started talking about this narrowing of the window thing, of getting closer and closer values to like smaller and smaller windows of values to find average rate of change. We just kind of introduced the idea. So today we're going to introduce limits, which are our technical mathematical way of doing that. And so hang tight. It's going to be a little idea-y in the beginning, but then it's going to get to a step-by-step information. All right, so here's the basic idea with limits. I wanted to have a question where limits would make sense before getting to calculus stuff. And so the question I asked is, what's the y-intercept of this function right here? And y-intercept, you just plug in 0 for the x's. But when you do that, you get undefined. And so that tells you there isn't a y-intercept. But if you look at the graph, then it's a little more interesting than we thought, than it might seem otherwise. Because when you look at the graph, boy, it looks like there's a y-intercept. I mean, here's the graph of this thing. I graphed it in Desmos, and it's like, wow, it looks like there's a y-intercept of, I don't know, it looks like about 1.5 is where it is. And it's like, yeah, it seems like it. But if you graph this on your calculator, make sure you're in radians, like switch your calculator to radians and never take it off radians in this class for the rest of the year. But once you do that, then you trace there. If you trace to 0, you get undefined. But if you trace close to 0, you get a number, and it looks like it's pretty close to 1.5. And you could look at a table also. And if you look at a table doing the same idea of what's happening really close to 0, then really close to 0, you can see the numbers are getting really close to 1.5. This is approaching on the left-hand side when x is a little bit less than 0. And this is approaching on the right-hand side when x is a little bit greater than 0. And then it's just getting closer and closer in. It's like, wow, it's getting really close to 1.5, even though there isn't a point at 1.5. Weird. So, and so this is what limits were made for. It's to deal with these situations where at a certain value, something is happening, but close to a certain value, it could be different. And we want to ask about close to the value instead of at the value. At the value, we can just plug the number in, but close to the value, we need a way to ask that question. And that's what limits do. So this is what a limit expression looks like, is you see the lim, that's short for limits, and you see this one. And so this is telling you what's happening to x. It could be x, it could be t, you can have any independent variable that you want. So, but it's x here, but it doesn't have to be x specifically. It has to be whatever the independent variable is. And then you've got this expression. So this is the expression we're wondering about. So this is what's happening to x. X is getting closer and closer to 0. And our question is, does this get close to something? Sorry about the handwriting. I promise ones where I don't read it out loud, I'll make sure to write clear. So and so does that get close to something? And so you can look at that. That's the y values, or that function. And we saw earlier what it was. These things are getting closer and closer to a number. And so if yes, that's what the answer to the question is. That's what the limit is 1.5. Now, the table we had earlier doesn't prove it's 1.5. I mean, maybe it's 1.49991 or something weird. I don't know. But you can see it's like, wow, that's getting really close to 1.5. And you see the 3 and the 2, and you kind of go, I bet it's 1.5. But we wouldn't know it for sure based on either the table or the graph that it was 1.5 itself. It could be something really close to 1.5 or something. But that's what the answer is. The answer is, what is that thing it's getting closer and closer to when you plug in these values really, really close to whatever x value you're curious about? And so we're going to be seeing how to evaluate limits today. And there's three basic ways to evaluate limits. One is from a graph. So what is it getting close to? And just look at it. There's from a table. What are the y values getting closer to? And you can look at the table. But the way that's more than just looking is doing it algebraic. And this is going to be a step-by-step process that we're going to run through. So I'm just going to run through it, and then we're going to see a bunch of examples. So first, you substitute what is it approaching? What is x approaching? And you substitute that in and see what happens. Okay? If you can substitute it in and you get an answer for 99% of the problems you'll see, that's the limit. And we'll show you that in a second. But if you substitute and you get 0 over 0, so now we're in this one. If you get 0 over 0, this is called an indeterminate form. Indeterminate form. It means, and it means you have to do something else because it's not giving you an answer to the question. If you get a different number, something other than 0 over 0, then then the limit is not defined, is undefined. You can also say there's no limit. You could say, the limit is not defined. There's no limit. There are some other answers, but we'll talk about that a little bit later. But basically, it's like there is no number to this answer to this question. So let's run through the examples. So this is the step-by-step process you can go through. So you see a limit problem. First thing you do, plug it in. So I plug in 2 for the x, and I get 3 times 2 plus 1, which is 7. Cross it to make it look more like a 7. Kind of. That's the answer to the question. You're done. Okay, what the heck is going on here? Like, what's happening? Well, what's happening is we've got a function that's just a line. And sorry, that's a y-intercept of 1, trust me. And so if you go to the point here when x is 2, if you get really, really, really close to x being 2, then the y values are getting really, really, really close to 7. And so this was a thing I said earlier. If you can substitute in and you get an answer, that's going to be the limit most of the time. And that's what's happening is that most graphs are connected. Like if you plug a number in to a graph, then like really close to that number, you're going to tend to get things that are really close to that value. And it's going to be kind of difficult to find ones where you don't. We will have many later on so that you can see why that would happen. But it's going to have to be kind of a weird function because there aren't a lot of times when you can get a value at one number and then you go a fraction of an inch over and then suddenly it's like, whoa, something totally different. That's unusual. So and so that's why the 99% thing I said, that wasn't a technical number. I just made that up. But that's why you can just plug it in. Like, oh, these problems are awesome. And then, I'm going to fix my notes before you get it, but that should be a 3. And so copy and paste. And so you could plug 3 into this one and go, oh, limit, x approaches 3, plug in 3. When you plug in 3, you get, when you do x squared minus 4x plus 3 over x minus 3, and you substitute in x equals 3. This is how we write that to be able to say that. Take this expression and put that number in, then you get 0 over 0. Indeterminate form, doesn't tell you anything. Okay, so I have to do something. And basically, it's going to be doing some sort of simplifying algebra is what I need to do. So I take a look at it and I go, okay, and it should be pretty clear to you what is intended here. This is a nice, easy problem. If you get this one, you're like, yay, easy problem, And so it's x minus 3 over x minus 1 over x minus 3, and I simplified it. Now remember what I said earlier. I said, so try something else, do a little algebra, and then start at the beginning. Okay, can you plug the number in now? So you go, okay, I'll plug the number in now, and I can plug it in. I can plug the 3 in, and I get 2. And that's the limit. Okay, what's going on here? Well, this graph is kind of interesting because this graph basically looks like this. Except, it looks like a line, except when you have x being equal to 3, at that one moment, there's a gap. I can't do that. I can do that on a whiteboard, but I can't do it on here. I have to redraw it. I can't erase a space. So there's a gap right there. So this expression we have right here is exactly equal to x minus 2, except at the number 3. That's the one time it's different. At x equals 3, this function we had in the beginning is undefined. But if you plug in any other number but 3, then this expression is exactly equal to the simplified expression we came up with, which is x minus 1. So because we don't care what's happening at 3, we care what's happening close to 3, then simplifying it is totally fine, because the fact that these two functions are slightly different, they're different only at 3, doesn't matter to us at all, because a limit question is saying what happens as you get close, not what's happening right there. Weird, I know, but there's a point to it, like why we're doing this stuff. So therefore, what we did is we simplified it. So we turned it into a graph where, well, just to make it easier on myself, where that point was filled in, and then we could plug it in. So we simplified it, and by simplifying, we changed the function a tiny bit, and now we can plug in that value. Weird. So that's the answer. The answer is 2. And so if you can do if you get 0 over 0, you go, oh, indeterminate form, do some algebra. You do a little algebra, and then you see, oh, now I can plug it in. Great. Here's the next one. Limit x approaches 0, tangent x over sine x. What's going on there? Well, if you simplify this one, then, and this is where those trig identities come in that I asked you to review, sine x over cosine x over sine x over 1. You should be really comfortable with doing fraction algebra like this, where you have fractions over fractions. And so, okay, this is gonna be kind of a funny thing, but what I call this, the simplifying thing you do here, is I call it flippy trick. What do I mean by that? Well, you're gonna multiply by the reciprocal. So what we're gonna work out is sine x over cosine x times 1 over sine x. Right? Multiplying by the reciprocal to simplify a complex fraction. Well, so what I'm imagining is this expression going kind of like that. The 1 ends up in the top, and the sine x that's in the denominator, that ends up staying in the denominator. And so I call that flippy trick. Anyway, I'll say flippy trick a lot. You got to get used to it. All right, I can cancel out the signs. Sine x is undefined at 0, but I don't care about 0. I want close to 0. And what do I get? I get the limit as x approaches 0 of 1 over cosine x. Okay, let's go back to the beginning. What does it say to do? It says plug in the number. I can plug in 0 into this expression, and now I can get an answer. I get 1 over 1, which is 1. All right, the next two I'm gonna have you try on your own here now. So this one here is a pretty tricky algebraic one, but I'll give you a hint. What you want to do is you want to combine the top into one fraction. Don't multiply anything out. Leave things factored, but combine the top into one fraction. Do a little flippy trick and see if you can cancel stuff, and eventually can you plug in 0? Because in the beginning you get 0 over 0. On the second one, I'll tell you the trick on this one. Whenever you see radicals in the numerator like that, a good thing to consider is assuming it's an indeterminate form, which it is, then you multiply by the conjugate. So square root of x plus 2 on the top and over square root of x plus 2 in the bottom. So try to work out these limits, do the algebra that it takes to get the correct answer. I'm going to stop the video here because I'm running out of time, and then I'll show you the answers. But you should try them out yourself. If you're stuck on it, that's totally cool. We'll show you the algebra, but you got to try hard algebra sometimes in order to be able to see what kinds of mistakes you make. So try these out yourself. Don't spend a ton of time on them, and the next video will show the answers. Okay? Good luck.